Hey, we are revisiting El Nino after a while. The way I record it, I just find the best papers and record them, and I haven't been looking at El Nino much recently because a lot of it has been about climate change, and El Nino is, of course, an internal variability, mode of internal variability in the climate system, and questions are about how this internal variability is being modulated by global warming. We don't have a very clear answer, but we are coming back here to diverse timing of El Nino onset linked to preconditioned recharge state and occurrence of westerly wind bursts. If you know El Nino, you probably know these terminologies already. If you don't, no need to panic. I have a bunch of El Nino podcasts and lectures as well. So El Nino happens in the tropical Pacific. Eastern tropical Pacific is generally cold. Once in a few years it gets warm, and the west, which is typically warm in the climatology, gets cooler. But this pattern is changing because of global warming. And the key questions are whether this is an unstable oscillation, which means it doesn't need any external kick. It just keeps oscillating, in which case the question is, why is it not very fixed in its periods? Happens somewhere between 2 to 7 years. Why such a large range of periods if it is unstable oscillator, or is it a decayed stable oscillator, which means something kicks it, it goes into a warm phase and then returns to normal or cold phase. La Nina is of course the other end of the El Nino. Warm, we call it El Nino southern oscillation, and so warm and so is El Nino, cold and so is La Nina, and so on and so forth. And then if there are triggers needed, then westerly wind bursts are one of those things. I have podcast on that as well. We'll see what that is, westerly wind bursts. And you probably know what a recharge state is. During normal times, trade winds are pushing the water west, and cold water is coming up because of upwelling in the east around, let's say, Galapagos and coast of western coast of South America, and warm waters are piled up on the western side. But if you average zonally, then the entire system is charged with warm water, and then something happens and that warm water is released. So the recharge state is generally considered necessary for the El Nino to go on, but there are papers arguing that that's not necessary. There is a thermal coupled mode, Walker mode, which can just work with sea surface temperatures without involving the subsurface ocean, the recharge and the thermocline, and so on and so forth. Okay, so considering all that, El Nino is generally phase locked to the boreal winter, December, January, February, but displays significant variability in its onset timing, contributing to its diverse climate impacts. Physical mechanisms driving this variability remain inadequately understood. This study demonstrates that the onset of El Nino events can occur over a broad range of months from March to September, with its onset timing closely linked to the precondition of oceanic recharged state and the occurrence of westerly wind bursts in the preceding spring. So December, January, February is the peak. Preceding spring is March, April, May of that 0 year. A stronger recharge state and increased frequency of WWVs promote earlier onset of efficiently transporting warm water to the equatorial eastern Pacific, supporting evidence from MEROC 6 simulations and a conceptual model underscores the crucial roles of both the recharged state and WWBs in determining the timing of El Nino onset, which has to be defined, which we will do. These results enhance our understanding of El Nino dynamics and hold important implications for seasonal climate prediction. If you are a new student and you start reading El Nino things, then you will see there are millions of papers, and it's often difficult to know if everything is understood. If so, why are there so many papers coming out? Or if we don't understand, what are the most fundamental questions that remain unanswered? And when you get smart enough, you will see that there are many very fundamental questions that remain unanswered. So these GRL articles tend to have a plain language summary for non-experts like you and me. El Nino, a significant climate phenomenon, arises from interactions between the ocean and the atmosphere in the tropical Pacific, profoundly affecting global weather patterns. Currently, predicting the precise timing of the El Nino onset remains a scientific challenge. In this study, we find that the onset of El Niños varies considerably, ranging from March to September. This variability is strongly linked to the preconditions of oceanic heat buildup, the recharged state, and the occurrence of westerly wind bursts. A strong recharge state and increased frequency of WWBs in the preceding spring can lead to an earlier El Nino onset by accelerating the eastward movement of warm water towards the central eastern equatorial Pacific. These findings deepen our understanding. And WWBs, westerly wind bursts, are they part of the system? They are often called multiplicative noise, which means they may very well start as just noise in the weather system because they are order 5 meter per second or more stronger, and they have to last about 3 days to be considered WWBs. We don't know exactly what the sources are of these. Could be coming from higher latitudes, could be part of the MJO, and so on and so forth, maybe from the southern Pacific, etc. But once they start, they can start pushing the warm water eastward, and then the convection associated with them can increase their fetch, the scale, and their strength, and so on. So when a noise becomes part of the system and begins to grow with the system, then they are called multiplicative noise. Okay, just a digression there. Let's read a bit of introduction and look at a couple of figures and then the conclusions. I'm going to be very brief here because the main point is again to come back and look at El Nino onset, pre-charge, precondition of recharge state, and WWBs. The El Nino Southern Oscillation is the most significant source of interannual climate variability, originating from large-scale coupled interactions between the ocean and the atmosphere in the tropical Pacific, and so has received significant scientific attention due to its far-reaching impacts on global climate. The rapid growth of ENSO events is largely attributed to positive ocean-atmosphere feedback known as the Bjerknes feedback in the equatorial Pacific, where a weakening of the zonal sea surface temperature gradient drives westerly wind anomalies. Westerly means coming from the west, so it is weaker trades, westerlies, anomalies. Further reducing the SST gradient, east-west gradient, cold-warm, and amplifying the system. I have a podcast on Bjerknes feedback separately that you can look up. Over the past several decades, various mechanisms have been proposed to understand ENSO's phase transition between its warm and cold phases, providing the theoretical basis for understanding ENSO dynamics and its predictability. It happens in the middle of the ocean. If it didn't do anything on land, maybe we will not care unless it's affecting fisheries, which it does. But since it affects weather and climate on the land a lot, we worry about El Nino and its prediction, right? The warm phase of ENSO, El Nino, is typically phase locked to the local seasonal cycle, with its development starting in boreal spring or summer, peaking in boreal winter, and decaying in the subsequent seasons. However, the onset timing of El Nino varies considerably, occurring between boreal spring and autumn. This variability in onset can lead to different global climate responses. For example, early onset of El Nino events can drive cooling in the eastern tropical Atlantic, a response less pronounced in late onset events. Despite the importance of El Nino onset timing, the underlying physical mechanisms driving this variability remain inadequately understood, which means, as I said in the beginning, despite having millions of papers, there are many important unanswered questions, which is good if you're starting research because you can jump on it. Definition of El Nino onset is needed. So westerly wind bursts I won't go into. It's 5 meters per second lasting for 3 days, and that's the definition. According to the definition from Climate Prediction Center, El Nino is identified when 3-month running mean of the Nino 3.4 SST anomaly, that's 5 degrees south, 5 degree north, 120 degree west to 170 degree west, exceeds the threshold of 0.5 degrees C for the last for the previous 5 consecutive months. Based on this definition, 11 El Nino developing years are identified for this study: 1982, 86, 91, 94, 97, 2002, 4, 6, 9, 14, and 18. 14, 15, 16 was, 15, 16 was El Nino, 14 was, by this definition was an El Nino. So this is for the period of 1980 to 2020. Given the variation in the zonal location of the El Nino onset, it's necessary to consider El Nino indices across different regions of the equatorial Pacific. Therefore, the onset of El Nino is defined when the area average SST anomalies in any of the Nino 4. So Nino 4 is more on the western side, 5 north, 5 south, but 160 east to 150 west, straddling the dateline, and Nino 3.4, which is more to the east, 5 south, 5 north, 170 west to 120 west, as we said already here, and Nino 3, which is a slight modification, 5 south, 5 north, 150 west, 90 west regions that then have to surpass 0.5 standard deviations for the onset. So let's read it again. The onset of El Nino is defined when the area average SST anomalies in any of the Nino 4, Nino 3.4 or Nino 3 regions surpass 0.5 degree standard deviations. There is no 3-month averaging applied here, but usually it can jump up and come down, so you obviously have to look at persistence for some time. So let's look at the results here. Here we are looking at the Nino 3.4 index for 1980 to 2020, and wherever you are crossing this 1 standard deviation red line, you have an El Nino, and below that you have a La Nina, and you have onsets identified here as May, August, or this is August, I guess. This is maybe April or May, and so on, but here it's an early onset in March, and so on. So idea is that even though the peak always happens in December, January, February, the onset by this definition seems to happen over a range of months from March to as late as September. In here, this one is September, August, and this is July, and so on. Okay, so looking at the westerly wind bursts and the sea surface temperature anomalies here, you have an early onset here. So onset happened here in April of year 0, and then westerly wind bursts are already there, and this is what we mean by multiplicative noise. As you can see, they get stronger. You can read that elsewhere or listen to one of my podcasts. When late onset happens, you see that onset is somewhere here in August, and then you have generally weaker westerly wind bursts and weaker and maybe shorter lasting. This is a time period over here, right? Going from July, August, almost June of year 0 into April, May of year 1, even though the strongest anomalies happen here in December, January, February. This entire thing is squished, and of course these are kind of composites of those years that we identified here. And is it possible that if it grows early, then the multiplicative noise by the westerly wind burst can make it much stronger El Nino than when it onset happens later? Okay, those are good questions. And honestly, every El Nino looks a little different, so we have to be careful about composites in any case. So recharge, so you are here looking at ocean heat content again for early onset and late onset El Ninos, and you are looking at the shape of these in the zonal direction in the deep tropics. So early onset precondition has lots of warm waters below the surface already coming close to the surface, whereas when you have late onset precondition, you do have stronger, subsurface warm water pool is available. It is beginning to extend eastward. This is going from western Pacific into the eastern Pacific, but you can see that there is a huge pool of cold water that's still sitting there. Sea surface temperatures are still colder because you have July, August, September as the strongest upwelling season anyways, but these are anomalies. So you can see there is actually colder anomalies, maybe stronger upwelling, even though El Nino is about to pop out. Okay, so we are looking at WWB frequencies again, early and late onsets. So you can see frequencies below normal, above normal here, and then they end up being similar once the El Nino does occur. But you can see these remain stronger and these remain weaker in frequency, and as we saw here, also weaker in amplitude. Okay, so composite time evolution of equatorial Pacific Ocean heat content anomalies during early onset, blue circles, so they are here. You can see the heat content is actually larger here, maybe in some definition, and this is already spread out, so it's weaker in some sense, but you can see that the growth rate here, or depletion rate, you can think of in terms of timing. This is going from January, February, March into October, November, December, but at the end they are close to each other. There is a bit of scatter, so you have to be careful. Okay, so late onset, orange bars and circles here. Bars denote the composite mean and circles indicate value of individual events. Black error bars represent the unstandard deviation, and yellow shading denotes the differences between early and late onset, which is happening here early on. And you can see in here again composite three-dimensional distribution of SST in shading, that's C. So let's look at B first. I'm being very haphazard here, apologies, and I have a call right now, so I have to take that as well. So that is Amazon calling. I still have a little pain in the ankle that may be gout. I don't know if you know what that is, but anyway, that's too much information. So we are looking at ocean heat content for early and late onset El Niños. Bars denote all that good things we already said. B is same as A, but for WWB frequency anomalies. Composite three-dimensional distribution of SSTs and WWB frequency given here in this far western corner. So you can see that westerly wind burst in general is much more active here than here, obviously, as we already saw here. And then they do some model analysis and model experiments to conclude that this is a real thing and not their imagination. At least their model they use, Mirok, which is the Japanese model, does confirm these findings. In the present day, we show that the El Nino onset timing exhibits considerable variability, with onset months ranging from a beautiful bird that I keep looking at, ranging from March to September. The onset timing is demonstrated to be closely associated with the warm water buildup and WWB activity in the equatorial Pacific during the preceding spring season. Early onset El Nino events okay, never mind. Early onset El Nino events typically emerging around April are usually characterized by a pronounced buildup of warm water and frequent WWB occurrence during spring of the developing year. The frequent WWBs can effectively transport the warm water eastward, fostering the development of SST anomalies and thus accelerating the onset of El Nino. There are waves involved which push the thermocline down, and there is advection part as well. Okay, so you have to be careful about what do we mean by transporting warm water eastward. Wave obviously travels much faster than advection in the ocean. In contrast, late onset events which tend to emerge around August are preceded by a weak recharge of oceanic heat in the equatorial Pacific with weak WWB activity. WWB activity, the weak recharge state and less frequent WWBs are insufficient to drive the eastward extension of warm water, delaying the El Nino onset. Our findings are further supported by the simulation of MEROC 6 model and a conceptual recharge oscillator model. This study provides a dynamical understanding of El Nino onset timing by focusing on the role of warm water buildup and WWB activity, thereby enhancing our ability to predict the diversity of El Nino events, particularly with regard to their onset timing. Here, diversity of El Nino is also seen as warming happening much more to the eastern wall versus, so let's say here, the warming is happening much more in the central eastern part, whereas this is shifted more towards the date line. So there is a lot of literature on El Nino diversity that you can look up. Okay, the warm water in the upper Pacific Ocean evolves gradually in response to surface wind variations via recharge-discharge processes. Compared to the slow oceanic changes, atmospheric variability exhibits a high-frequency behavior which remains less thoroughly understood. So another open question. Our analysis reveals that WWB activity appears to be closely associated with SST anomalies in the equatorial western central Pacific, a region situated near the eastern edge of the warm pool. This region is highly sensitive to SST fluctuations because you have, going from being above the convective threshold, deep convection in the atmosphere, to being colder. So sensitivity there is high and the front gets pushed. There are papers on this, and I've discussed this in the El Nino lectures I have as well on my channels. So even small anomalies at this sensitive region can excite substantial atmospheric convective responses due to the high background SST. The SST anomaly patterns in the western central Pacific exhibit a significant difference between early onset and late onset events, despite both displaying positive subsurface temperature anomalies near the thermocline layer, as we saw. In the late onset events, the thermal structure in the western central equatorial Pacific is characterized by a cooler surface and warmer subsurface. The cooling SST anomalies, colder SST anomalies and corresponding easterly wind anomalies exhibit occurrence of, inhibit occurrence of WWBs. What we mean here, you can see you have easterly anomalies and westerly anomalies here, and these can inhibit the growth or positive feedback of the WWBs onto the growth and the Bjerknes feedback. In contrast, in early onset events, warming from subsurface to surface layers in the western central tropical Pacific facilitates more frequent WWBs by enhancing deep atmospheric convection. That's what makes it multiplicative noise. This warming during boreal spring is proposed as a potential precursor to the development of super El Niños. However, the dynamics behind this SST warming is complicated. For example, the conventional relationship between sea level and thermocline depth is not evident in the central Pacific. Other studies suggest that non-linear oceanic processes such as ocean mixing could play a non-negligible role in SST variations. Essentially, you expect heat content to build up to correspond to sea level being higher, but sometimes you can have other ways of doing SST warming without a corresponding sea level signal. Not kind of a detail. Furthermore, frequent WWBs can amplify SST warming in the western central tropical Pacific by expanding the warm pool eastward. While we argue that frequent WWBs in the early spring contribute to the early onset of El Nino events, the question of whether SST anomalies predominantly drive WWB activity or if WWBs initiate these SST warming remains an open question that deserves future investigation. So it's a nice new point, but as you can see, there are still many unanswered questions. So you keep on adding little bits of information each time, but the fundamental understanding of what are WWBs, why do they occur in the West, and when do they play an active role, and why are there many years where WWBs happen but El Nino doesn't happen? Is it just to do with preconditioning the recharge state, and so on and so forth? Okay, so let's leave it here.